Real training data does not arrive as one perfect tensor. PyTorch Dataset and DataLoader turn messy examples into clean batches. This is the workflow you'll know how to run when we're done, which builds a dataset from raw records and trains through batches with a loop. I'm Professor Pi, teaching AI foundations with simple Python. Real projects start with messy rows, CSVs, JSON blobs, and a few missing values. The goal is simple to state and hard to forget. Turn those rows into examples you can reliably shuffle, batch, and feed into a model. Dataset and DataLoader handle that plumbing. Memory, indexing, batching, and how samples become tensors. For a quick experiment, they save time. For larger runs, they save you from subtle bugs and wasted compute. Think of dataset as the indexed view of the raw table, and DataLoader as the machine that samples, batches, and collates those rows into train-ready tensors. To make this concrete, we'll walk a short path, one paired sample, then a batch of 3, then a collated batch shaped exactly for a training step. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we will move raw table rows into PyTorch tensors, so indexing is straightforward. This example converts a tabular toyset into tensors using PyTorch, so we can inspect one paired sample quickly. The tensor constructor packs 4 short feature vectors into a float 32 matrix and stores the integer targets alongside, keeping positional ordering intact. TensorDataset then zips the feature matrix and label vector into an indexable object, so any if lookup yields matching tensors without extra bookkeeping. Accessing dataset 0 retrieves 1 feature tensor and 1 label tensor, mirroring the pair structure students usually manage manually with lists. The printed output shows the very first feature pair and label, confirming that our raw table now lives in PyTorch form. Tuples are fine, but we often need extra per row info. Next, we wrap those tensors so each sample can carry lightweight metadata. This snippet wraps the same tensors in a custom dataset subclass, so we can attach lightweight metadata to each row. The initializer stores the feature and label tensors, and asking for len custom ds reports how many samples the object can expose. The item lookup builds a small dictionary containing the tensors and a quick sum of the feature values, demonstrating how to compute per sample helpers on demand. Instantiating tabular dataset keeps our tensors in memory, but now every indexed read returns a richer dictionary instead of a bare tuple. The printout confirms that the dataset spans 4 samples, and that the third entry carries the expected feature sum, so the extra metadata is ready for loaders. Now we need to group rows into mini batches and inspect aggregate values across them, so we use DataLoader to handle batching and iteration. This code uses torch.utils.data.DataLoader to batch our custom dataset and locate the largest feature sum in the first mini batch. DataLoader receives the dataset with batch size equals 3, so it collates the first 3 dictionaries into stacked tensors plus a tensor of sums. Calling next_iter_loader materializes that batch and lets us keep the sum tensor separate to analyze how individual rows compare. Using a larger batch size would widen the comparison to more samples at once, while a smaller batch would focus on fewer rows. Torch.argmax pinpoints the index of the maximum sum, and the printed index value pair shows which sample currently has the strongest combined features, giving a quick quality check before training. Batched dictionaries are fine, but training code usually expects fixed stacks and perhaps a summary statistic. So we add a custom collate function to shape each batch exactly. This example supplies a custom collate fun, So torch.utils.data.DataLoader can reshape each dictionary batch exactly how our training loop expects. Inside collate batch, we stack feature tensors and label tensors separately. Then compute a float sum average that summarizes the batch's feature intensity. Returning the dictionary with those tensors plus the average lets downstream code access structured data without rebuilding the stacks. Increasing batch size would smooth the average across more samples, whereas a smaller batch would make some average closely track individual examples. The printed average and labels list confirm that the custom collation keeps 3 examples together while adding a ready-to-use summary statistic. Finally, we connect the collated batches to a small model and run one optimization step, so you see the full flow from raw rows to parameter updates. This snippet runs a single pass of SGD on the data loader to show how a PyTorch model consumes the batch dictionaries. We create a linear layer with 2 inputs, zero its weights and bias, and hook up torch.optim SGD, so optimization starts from an easy baseline. torch.nn.functional binary cross-entropy with logits compares the logits to label tensors that we cast to float column vectors. Iterating over train loader feeds each batch into the model, runs the backward pass, and steps the optimizer in place. Lower learning rates would change the loss more gently, whereas higher rates could overshoot this tiny dataset and destabilize the updates. And the printed final loss of 0.68 reflects the mean training loss after the pass, confirming that the update moved the model away from its initial state. In a real project, you would map these pieces to disk reads, pre-processing pipelines, and larger models. The dataset is where you normalize, impute, or augment. The data loader becomes your throughput control knob. The collate function encodes whatever shape the model expects. Quick recap. Wrap raw rows into dataset objects. Use DataLoader to batch and shuffle, and return collated tensors your loop can consume. Reach for this pattern when you want predictable batching, shuffling, or per sample metadata. One caveat: if your transforms are heavy, the collate step can become a bottleneck. So measure and move work around if needed. Next step, scale this pattern to a larger corpus and add timing and accuracy checks while experimenting with batch size and learning rate to find a good throughput versus convergence point. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.